Good evening. All right. So we'll start with the main topic of groups today. But before that, before I actually define what a group is, we'll start out with some motivational examples. Some examples that are groups, and we'll try to arrive at what a group is by looking at the example. So the model for groups is actually the set of integers with addition operation. So the first example is the set of all integers, which I will denote by this letter Z, with the operation addition. And we look at what properties the elements have when we are adding them. So the first property we look at is that if we add two integers, so this addition is a binary operation, that is, it acts upon two elements at a time. When you add two integers, we get another integer. So adding two integers will always give you another integer. You can't get a rational number by adding two integers, or you can't get a real number by adding. I mean, every integer is a rational number, but it will still stay within the same set. That is, if you take two elements from the set Z, then their addition will be an element in the set Z. That is one important property that integers have when you look at addition. For example, 3 plus 2 is 5 and 5 plus minus 2 is 3. You always end up getting addition. Another nice thing about the set of integers is the zero element. That is zero in the set of integers. And zero is a special element. What's special about it is that for any other integer, or for zero also, for any integer n in z, when you add 0 and n, and since you can add in either order, you'll get the same thing for addition in integers. N plus 0 is 0 plus n is equal to n. So adding 0 to any integer gives you back the original integer. So this type of element is called, the 0 is called the additive identity, or the identity element for addition. Then the third important thing about the set of integers is that every element has an inverse element. And what we mean by an inverse is, given some element, let's say 5, there is some element such that when you add those two elements, you get back the identity element, which is 0. So for any n in Z, minus n is also an integer, and n plus minus n is 0, which is the identity element. So this type of property is held by every integer, and for 0, minus 0 is simply 0, so the inverse of 0 is 0. Another interesting property that these integers have is, if you take integers a, b, and c, then if you first add a with a and b, and then add c to those two, to the sum of a and b, that will be the same as first adding b and c and adding that to a. So an expression of the form a plus b plus, you can write the expression, the sum of three integers. So plus is only a binary operation, so it operates only on two integers. But you can write a plus b plus c unambiguously for three integers, because regardless of the order in which you carry out the operation, you'll get the same result. So these properties have names in mathematics. The first property that we saw is called the closure property. So you have a set and an operation. When you per and a binary operation. When you perform the binary operation on two elements of the set, then the result is an element within the set itself. That property is called closure. The next thing, this I already mentioned, 0 is called the additive identity. And if it's not addition, if it's some operation, it's still called the identity element of that particular operation. So an identity element exists for Z under addition. Then we have the existence of inverse for every element in the set. And the last property, that is uh, order in which you carry out the operation, is irrelevant. This property is called associative, or the associative property. This is the main example or the main model on which we'll understand groups. Then let's look at a second example and see if that also has these kind of properties. And this example is, consider the set S equals to 1, 2, and 3. Now consider all bijections from S to all bijections F from S to S. So how many bijections will be there? Yes. Yeah. So there are six functions in this set. For now, I'll just call it capital F. We'll give it a name later lectures. So the elements of the set F, the set of all bijections are, there are only six, so I can just list them. So let F1 be just the identity function. The element goes to itself. F2, it changes 1 to 2 and 2 to 1. So such a change of two elements is called a transposition. So it transposes 1 and 2. Uh, Transposition is just a swap. F3, let's say 2 remains fixed, but 1 goes to 3 and 3 goes to 1. F4, 1 is fixed, 2 and 3 are swapped. So these three operations fix, F1 fixes all the elements. So none of the elements change under the function. F2, F3, and F4 fix one element each. F2 fixes 3, F3 fixes 2, and F4 fixes 1. And it swaps the other two elements. Another type of function would be sending 1 to uh, 2, 2 to 3, and 3 to 1. So it changes all three elements. It is kind of adding 1 in a circular fashion. Finally, 1 can go to 3, 2 can go to 1, and 3 can go to 2. So these are the six functions. So these are the elements of the set F. So F is a set that contains all the bijections from S to S. The operation that I will consider is the composition of functions. Function composition. We know that the composition of two functions from S to S is another function from S to S. But there are only six possible functions from S to S, so it must be one of these elements. So the composition is closed. It is closed For example, F2 composed with F5, what will it be? So 1 F5 will send 1 to 2. Then the 2 is sent to 1 by F2. So 1 is sent to 1 by the composition of these two functions. Then F5 sends 2 to 3 and F2 sends 3 to 3 itself. So F2 composed with F5 sends 2 to 3. And F5 sends 3 to 1. F2 sends 1 to 2. So F2 circle F5 sends 3 to 2. But if you observe, this is nothing but the function F4, which fixes 1 and swaps 2 and 3. So the composition of two of these elements is again an element of the set F. We have defined, this is nothing but composition of functions that I had defined in yesterday's class. So we had defined f of g as a function which sends the element x to f of g of x. So first you consider g of x and find, evaluate f at the point g of x. That's by definition of composition. So now this composition of functions is closed. Of course, I have done with one example, but you can go and, but we already saw that composition of two one-to-one functions is one-to-one, and composition to two onto functions is onto. So composition of two one-to-one and onto functions will also be one-to-one and onto. So it is also a bijection. Then what is the identity element? The identity element is F1. F1 is the identity. Why is that? That's because for any function Fn, Fn circle F1 is nothing but Fn, which is also equal to F1 circle Fn. Then what is the inverse of any function? Consider F2 circle F2. We can abuse the notation, and instead of the circle, we can simply write it as a product. And notation, I'll explain it in my future lecture. For now, you can write this as F2 square, which means simply F2 circle F2. If we do this, what will you get? F2 swaps 1 and 2 and fixes 3. Now, if you apply F2 again, then you are swapping back 2 to 1 and 1 to 2, and you're still fixing 3. So, if you apply F2 twice to any element, then you get back the same element. So, F2 square is nothing but F1. So, the inverse of F2 is F1, F2 itself. Similarly, for any function that swaps only two of the elements, the inverse is just swapping the two elements back again. So F2 is the inverse of F2, F3 is the inverse of F3, and F4 is the inverse of F4. And you can verify as an exercise, you can try this yourself. f5 and f6 are inverses of each other. Then finally, for any general function, not just this function, function composition is associative. So again, this set capital F with the operation composition of functions is similar to the set of integers in that the composition of two functions in this set is another function in this set. There is an identity element f1 and each element has an inverse. And finally, it is also associative. So these four properties are held by both the set of integers under addition and the set of bijections from 1 to 3 to 1 to 3 under function composition. The third example this follows. Consider a triangle like this. Let this be the center point. Now consider this is an equilateral triangle. Consider the rotational symmetries of ABC. So a rotational symmetry of a plane figure would be some motion that you do with the plane figure such that, so suppose you have a sheet of paper, you cut out a triangle from that paper and you do some motion on that paper and put it back in its place. So what are the different types of motion you can have when you do that? Those are the symmetries of the figure, and rotational symmetries are if you take the triangle out of the plane and then rotate it along the center and put it back in the same place where you had taken it out, those would be those are our rotational symmetries. What I mean to say is you can take this triangle ABC and you can rotate it like this. Now these two triangles you can actually place them one on top of each other so that you couldn't distinguish between the two shapes. So if you had cut out this part, that's only the triangle part from a sheet of paper, rotated it and put it, you could still put it, rotate it by 120 degrees. You could put it back in place, except that now in the place where there was vertex A, you have the vertex C. In place where you had vertex B, you have the vertex A, and in place where you had vertex C, you have vertex B. So you have actually rotated it and changed the position of the vertices. But if the vertices are not labeled, you could. So this angle is 120 degrees. with respect to this line, this A, uh, this is the axis of rotation, this is the origin. So you have actually rotated. A was at the on y-axis, now it's on this axis here. So you actually rotated it by 120 degrees, right? What is rotation? There's an x-axis, there's a y-axis like this, x and y-axis. Now A is at a 90-degree angle, right? So if you had a ray like this, then you rotated it by 90 degrees to get A. This angle was 90 degrees. Then you rotated the triangle around the origin. And the new angle is 90 degrees. This whole angle is 90 degrees plus 120 degrees. So you actually rotated this ray by 120 degrees to this position around the center point, around an axis that is perpendicular to the plane. So there is one axis that is coming out of this center point and it is perpendicular to the plane. Then you are rotating about that axis. That is one type of rotation you can do. So these are the rotational symmetries. So if you're rotating it again by another 120 degrees, like this, actually you can see the angle, right? It's showing a text. Is it visible? Yeah, here it's showing the angle that you are rotated by, right? It's showing 240 degrees. Yeah, so now I have rotated by 240 degrees. And when you rotate by 240 degrees, your A, which was here, you rotate by 120, it will go to this position. Now another 120 degrees, it went to a different position. But it's still, if it was unlabeled, you couldn't actually distinguish between this and this, right? It's still in the same position per se. Only because only if you label it, you will know that the vertex has changed position. So that is another rotational symmetry. Now if you rotate it again by another 120 degrees, you will get back the original triangle. So there are, in a sense, three rotations you can do. The first rotation is you don't actually rotate it at all. That is the identity. You keep it as it is. There is rotation by 0 degrees or rotate by 360 degrees. You can take it either way. The second rotation is rotate by 360 by 3 into 1, rotate by 120 degrees. I'll call that R1. R2 is a rotation by 240 degrees with respect to the original 0 degree rotation. Now you consider the set of these three operations. So if you compose again, this is actually a kind of function from points in the plane to points in the plane again. So this rotation is actually a type of function. So its composition is again closed. Or else you can understand it as if you rotate by, if you take any two rotations and do them one after the other, you will end up with one of these rotations in the end. So if you rotate by 120 and then rotate by 240, you will end up having rotated the entire thing by 360 degrees in the end, which is same as rotating by 0 degrees. So you'll get R1, R2 is R0. If you rotate by 120 and again rotate it by 120, R1, R1, that is nothing but a rotation by 240 degrees. So R1, R1 is R2. So this operation again here we'll call it composition. Composition is closed. Identity is R0. What is the inverse? The inverse of R0 is R0 itself. If you rotate by 0 degrees twice, it's the same as not rotating at all. What is the inverse of R1? It is R2. It's closed. R0 is the identity. Inverse of R0 is R0. R1 is R2 and inverse of R2 is R1. And it's also, you can also check that it is associative. Since it's just rotation, if you do RA, RB and if you do RC first, RA, RB first and then RC, it's the same as RA times RB, RC. So this is another example of a set with an operation where the set operation is closed. There is an identity element for the operation. Every element has an inverse under that operation, and the operation is also associated. Now, the next example I wanted to give was symmetries of a square. But if you're finding it difficult to understand, finding this too hard to understand, then I will skip that example. So, should I do that example or no? Okay. Yes. That is also a valid. Uh, that is also a valid symmetry of a triangle. Uh, so if we include that, then that would be the kind of the next example. It's called a dihedral group. So this is not just for a triangle, for any regular polygon with number of vertices n greater than or equal to 3, you can form a set of such symmetries. There will be 2n elements in that, 2n symmetries, and n of those symmetries are just rotations. So rotation by 0 degrees, rotation by 360 by n, rotation by 2 into 360 by n, up to rotation by n minus 1 into 360 by n degrees. Each of those will give you back the same figure with only the vertices changing positions. So again, for a square, this would be, for a square, if you label this as W, P, G, B, white, pink, green, and blue, then if you don't rotate it, it will be simply rotation by 0 is the identity. Then you can actually rotate by 90 degrees, like this. So this is showing clockwise, okay, but you can do it clockwise or counterclockwise, it will be the same. So this would be a 90 degrees about an axis that is perpendicular to the plane, but at the center of the square. This is R0, this will be R90. So this is one type of operation, a 90-degree rotation. Then you can rotate by 180 degrees or 270 degrees, then 360 degree will get you back the origin of the world. That is one type of operation. And the other type of operation is, so here there is a difference between polygons with odd number of vertices and polygons with even number of vertices. For a triangle which has odd number of vertices, you can take this ABC and then you can draw an axis from a vertex to the midpoint of the opposite side. Then you flip about this particular axis. Then what you will get is, so I am flipping about an axis from a vertex to the midpoint of the opposite side. So what I would get is C, E, A, and B. This is another type of plane symmetry, and it's not, you can't get this by any type of rotation, right? So from the rotations, you can see that this is just B, C, A. So this is a type of plane symmetry that is not a rotation. And you can flip each of these rotated triangles in this way. Or you can flip one triangle about three different axes. So from each vertex, you drop a line perpendicular to the opposite side. Since it's an equilateral triangle, a line from a vertex to the midpoint of the opposite side is at 90 degrees with the opposite side. So you can flip about any of these axes, and each of the flips will give you one type of symmetry or a bijection. The difference with this case, in the square case, is that there are two such types of operations you can do. One is uh, you take the square and then you draw a line from the midpoint of one side to the midpoint of the other side, and you flip about the axis that joins the two midpoints. Then you would get the figure W would be here, P would be here, this would be G, and this would be B. So this is a symmetry of the square. Another type of operation you can do is instead of the axis from flipping, let me just show it. Um, so this would be this is a rectangle, but assume that this is a square that I have. I'm keeping it in a plane like this, or I can keep it in a plane like this. So by rotation, I mean rotating it this way, right? So the vertices are changing like that. By a flip, I mean changing it this way. Now, assume this was a clear a glass plate instead of a solid block. Then you would still be able to, and if you paint or write the letters or paint only one side of it, the corners on one side, if you paint those with P, W, PG, white, pink, green, or blue, if you flip it, what happens is the colors are on the opposite side now. So initially, when you had it like this, the color was on this side, but when you flip it, it actually went behind. But since it's a transparent glass, you can still see the color. So you can still kind of identify where the uh, which vertex is at which corner, right? So a flip is like this, and you can flip about. So this would be a horizontal axis. You can flip it like this. This would be a vertical axis. You could flip it like this. right? Another type of flip would be along this diagonal. Suppose it was a square, then you could flip it along the diagonal like this. But here it's not a square, so it doesn't work out that well. But you could flip it around the diagonal also. So now the thing to note is that when you do these operations, you get back the square shape again. So it doesn't change, and the square is still in the plane in which you started it from. So you have to go back to the original plane where you were. And it's still a square, except that the position of the vertices is changing. So a diagonal flip would do what? It would keep the P and B vertices at the same point. It would flip the G and W vertices. So for a polygon with even number of vertices, there are two different kinds of flips you can do. One kind of flip is through an axis that passes through midpoints of two opposite sides. Another kind of flip is an axis that passes through two opposite vertices. But here for a triangle, you would have only one kind of flip, that is through an axis that is passing through a vertex and its opposite midpoint. So here there are, for a square, there are of these axes that pass through midpoints of opposite sides and two axes that pass through two opposite vertices. So there are two diagonals. So again, you are still left with only four different flip operations. And here for the triangle, you are left with three flip operations. So for a polygon with n vertices, there are n flip operations and n rotation operations. And each of these operations will only change the position of the points, but so the orientation of the points has changed, but the figure is still the same figure that you started out with. So this, along with the operations that I showed here, is called a dihedral group of order 2n for a regular polygon of n vertices. And this type of group is more useful for people who are concerned with geometries of figures and artists, designers, and when we are dealing with the orientation of molecules and all in chemistry, these type of symmetries and symmetric groups are important. Okay, so these are just some motivational examples of where why we are looking at groups and what are the properties that we are actually interested in when we are looking at groups. The four properties that we had identified. All these sets are very different, right? So the set of integers, the set of bijections from a group of n natural numbers to n natural numbers, and the set of symmetries of a regular polygon, they're all very different sets with very different operations. But they all have the same kind of properties. So what we want to do in abstract algebra is to determine a certain, for a given set, determine whether that set has a particular group of properties. And then once we have fixed an idea of a group or fixed certain properties, we'll say that any set and operation with those properties is a group. Once that is done, we'll completely do all our analysis only by considering the structure of the group and not the particular group itself. So it is a kind of abstraction. For example, uh, in electrical and electronics, when we study circuits, suppose you have a circuit which has a power supply or a battery or something, and then a bulb here, then you want to figure out how much current the bulb is drawing. In that case, actually, if you want to solve this problem rigorously, then you will have to use the four fundamental equations, the Maxwell's equations that you have for electromagnetism. You will have to write down the electromagnetic equations for this type of circuit, uh, say with a loop, Ampere's law. I don't remember the exact formulation, uh, with the electric field and magnetic fields and all. And then you will have to solve this problem. But that is a very tedious process because this bulb can have any shape. This is an incandescent bulb, then it will have a tungsten filament that is going like this, like swirling around inside an incandescent bulb. Or if it's some other circuit, uh, let's say your iron box or an old school boiler which has a, uh filament that has a coil like this, or some other type of equipment. What we are interested in studying is the amount of current that is going through the circuit and the potential difference between 2 points in the circuit. So to study all that, it is very difficult if for each new different element, like maybe an electric iron box or a bulb or whatever it is, to carry out the analysis each time using Maxwell's equations would be very difficult. So what we do is we abstract out some properties of this bulb that we are interested in and model this as simply a resistor. And we model this power supply regardless of what that power supply is, whether it's a nickel cadmium battery or lithium ion battery, whatever it is, as some power supply such that it provides you a particular fixed voltage, say 5 volts, and this resistance, and this is some element that has some resistance, for example, 5 ohms. And then we'll find the current using different laws, like if it's an ohmic element, ohmic resistance, and V equal to IR, we can find the current like that. But what we are doing is we are moving away from a concrete power supply to an abstract version of the power supply that only gives you the properties that you are interested in. What we are interested in here is only the voltage and maybe the internal resistance of it. We don't care about the mechanism in which the voltage is being delivered to us, whether it's through a chemical process involving lithium ions or it's a nickel cadmium battery or it's a hydroelectric power, or it's coming from some other type of power source. We don't care. What we care about is the voltage that is provided and the internal resistance. Similarly, here, this we don't care what element this resistance is coming from. We only care that it is an ohmic resistance. So is it a filament that is swirling around? What is the structure? Is it dissipating? Is it giving out light? Is it just dissipating as heat? That is not important to us. So we are kind of taking out the important aspects of it and abstracting these elements using only the resistance property or the voltage. So in a similar way, instead of looking at the group of integers or with operation addition or the set of symmetries of regular n-gons with composition or the set of bijections from 1 to 3 to 1 to 3, we'll take out only the properties that we are interested in and we'll start working only with that abstract notion of those of the set, its operation and the properties that the operation has, and they will derive useful results without looking at which operation or which set uh, we are actually interested in. And when you're trying to apply it in certain scenario, then you bring in the set and the operation and go ahead with your analysis. So that is the point of abstract algebra. And the first structure that we study in abstract algebra is groups. So we'll begin with till now we only saw examples. Now we will begin with a proper definition of a group. But before that, we'll define what is a binary operation. So let G be a set, a binary operation on G is a function that assigns to each ordered pair of elements of G an element of G. So this closure property that we had with the operations that we saw till now, we'll include that in the definition of our binary operation. So make the we won't state the closure property as a separate property of a group. We'll simply assume that we are working with a closed operation. Then we'll define a group as follows. Let G be a set together with a binary operation star. Then we say G is a group under star if the first thing is there is an element E in capital G such that G star E is equal to E star G is equal to G for all elements in capital G. So this means that there is an identity element. Then every element for every element G small g in capital G, there is an element H in G such that GH is equal to HG is equal to, should I written this as G star H star G is equal to E. That is, every element in the group in the set G has a inverse. The third property is that this operation star is associative. For all G1, G2, G3 belonging to capital G, if you do G1 star G2 and then star G3, that's the same as G1 star G2 star G3. So you can unambiguously write this as G1 star G2 star G3. So a group is simply a set with an operation, with a closed operation, closed binary operation that has these three properties. Now, as we saw, in the previous, one of the examples that we had seen was the set of integers. No, we are only dealing with binary operations. Our model for this is the set of integers under addition. Yes, the binary means two, right? Yeah. Yeah, it is only a binary operation. We don't define groups for ternary operations. So similar to how we yesterday in the preliminaries we were saying invented or made we invented the imaginary numbers to solve an equation of the form x squared plus 1 equals 0, which could not be solved with just real numbers. So in the same way, these things this came up Um when Niels Abel was working with functions and their compositions. And we compose only two functions. Composition of three functions at a time is not really defined. So when you say a ternary operation, it doesn't always have to be uh, the application of a binary operation twice, right? You can have other types of ternary operations. So, for example, you could say a ternary operation which takes the operands is AB plus C. Now here there is no single binary operation that you're applying twice to get your ternary operation, right? So this would be entirely different. Uh, this is not the application of a binary operation twice. So we are dealing only with one of. Later, when you study rings and fields, what happens is you study, since integers have addition and multiplication also, then you can study a set with two different operations, addition and multiplication, with r plus having some properties and r and multiplication having some properties, and then plus and multiplication when you apply together having some properties. But that's still again not a ternary operation. We will deal with a set and two binary operations. So far, I have not really come across any ternary operation that gives a structure that's used anywhere. You could maybe get a structure with a set and a ternary operation, but as far as as far as this course is concerned, I, we don't deal with ternary operations, and I am not really aware of any structure which has ternary operations. We just don't deal with it in our field. Okay, then one more interesting thing to note is our integers had another property that we kind of left out, and we did left it out deliberately, and that was for all G1, G2 in the set G, if G1 times G2 is equal to G2 times G1. That is, if the order of the operation does not matter, then G is called an abelian group. It is named after a mathematician called Niels Abel from Norway, whose idea sparked the systematic study of groups. Though the term group and all these things actually came later, and he was not the one who named these things or studied these things as directly as groups. But he started using it for functions, and that's where the idea came from, at least in Western mathematics. Or you could also just call it a commutative group, because that property, that G1 times G2 is equal to D2 times G1, is called the commutative property. If a group is not abelian, we simply call it a non-abelian group, or you can say non-commutative. One thing to note that is this slightly an abuse of notation, because from our definition of a group, G is a group under star. So when you say a group, you have to mention the set and the operation. Because as you'll see, some sets can be a group under one operation, but not a group under some other operation. But here I have still written G is called an abelian group, which is not exactly right, but we assume that the operation is clear, so the context will tell us which operation it is. And with slight abuse of notation, we just say G is a group instead of G star is a group. If you really wanted to be precise everywhere, you could simply say G star is a group, or G is a group under star. Now we'll look at lots of examples just to hammer in the idea of a group and to introduce you to uh, groups that we'll deal with later, but just in a so just to get you familiar with groups, we'll do many examples. Example one, the set of integers z, which is actually our model for the group structure itself. Then you can actually check that the set of rational numbers will denote it by q. Q with this extra bar, like this, you'll just draw an extra bar. That's this notation because we can't have bold symbols when you're not when you're typing. You can just use a bold symbol or a calligraphic symbol, but while writing, we will write that to mean the rational numbers. And the set of real numbers are, so all of them are groups under ordinary addition. This is just the addition we learned in school. In all these cases, the identity is the number 0 and the inverse of x is minus x. Then the second example, which is actually a non-example or an example of something that is not a group, is the set of integers z under ordinary multiplication. Why is it not a group under multiplication? Yeah, yeah. So one is the identity, which implies property three faiths. 5 times anything equal to 1. No such integer exists. Then we said that it is not a group because fractions are not included in integers. What about the set of rational numbers, which includes fractions? What about q under ordinary multiplication? Is that a group? It is not a group. Identity is again one, no problem. It is closed, it is associative, no problem with that. When you're talking about inverses, for all elements it's okay except for one element. What is that element? This is under multiplication, right? Do all rational numbers have an inverse under multiplication? Inverse of 2 is 1 by 2. Inverse of 3 by 5 is 5 by 3. What about inverse of 0? Yes, 0 is the rational number, right? Q is defined to be set of all A by B, thus that A and B are integers and B not equal to 0. So 0 can be written as 0 by 1. So it is a rational number. So 0 does not have. Yeah. So Q times Q and Q under is not a group. So the next example would be, what if we removed 0, then Q star is the notation we will use for Q minus the set 0. This is the difference of two sets, A minus B. And most of the time I'll write this as Q minus the set. So this is another notation for the set Q minus the set with 0. Then Q star under ordinary multiplication is a group. Then consider the set 1 minus 1 I minus I, where I square is minus 1 under complex number multiplication. Is this a group? Here, one is still the identity because 1 times 1 is 1, 1 times minus 1 is minus 1, 1 times I is I, and 1 times minus I is minus I. So, 1 would, and 1 belongs to the set. So, 1 is still the identity. What would be the inverses? So, we'll have the element and its inverse. Yeah. Yeah. So, each element has an inverse. Of course, complex. So, one thing is that this is actually a subset of complex numbers, and I could have included. I will later do an example, but complex numbers under complex number multiplication is also a group. So that means the complex number multiplication is associative. So we don't have to check for associativity in this case. It's given. Then it's closed. We'll actually have to check that. But it is, since there are only 4 elements, you can write down all the operations. 1 times minus 1 is minus 1, which belongs to the set. 1 times I minus I, they all belong to the set. Then minus 1 times I is minus I, which is in the set. Minus 1 times minus I is I, which is in the set. Then I times minus I is 1, which is also in the set. So the set is closed. And we have the identity element and the inverses. So this is a group. And what are these numbers actually? 1 minus 1 I and minus I. Why did we pick this set? Any idea? But minus 1 and I, what's the, so what would be the fourth power of all these numbers? Yeah, so these are all the complex fourth roots of 1. Yeah, so the complex roots of unity. Complex, so this would be the complex fourth roots of unity. And by unity, I mean 1. Next, we'll see, so consider the set. So general procedure to show associativity, a lot of the times we'll just assume that it is true in most of the examples that we'll see here. But you just have to show the property. That's all. You have to show that A star B star C is A star B star C. So, for example, uh, 2 plus 3 plus 5 is you have to do the insider operation first. 5 plus 5 is 10, and then 2 plus 3 plus 5 is 2 plus 8, which is 10. So these two are equal. So these two are equal. Composition, it is true. It is associative, it is not commutative. Composition of functions is an associative operation. So to prove that it is not commutative, you have to uh, either from the property or the type of operation you can somehow show, or most generally to prove that it is not commutative, you will have to do it by counter example. You'll have to give an example to show that the operation is not commutative. For example, let's take the set of natural numbers with star defined to be a star b is a power b. In this case, you would have a star b star c is a star b is a power b, star c is a power b whole power c. This by law of exponents, this is a power bc. But a star b star c is a star b power c is a power b power c. And in general, b power c is not equal to bc. There might be specific elements for which this is true, but for example, if b and c are 2, 2 square is 4, is equal to 2 times 2, but it's not true in general. So associativity requires that this is true for all possible elements a, b, and c. But this is not true for all possible elements, right? So this star is not, it's not associative. Okay? Yeah. So the associativity of natural number addition and natural numbers and multiplication of natural numbers, even for multiplication of matrices, these things will take it for granted and we won't go into proving that. We'll uh, just from school we know that, but we won't go into in-depth proofs or any abstract proof. We'll just assume it. Even for matrices, for 2 by 2 matrices, you can still show it doing it by hand, assuming a general matrix A, B, C, D, E, F, G, H like that. And you can multiply out 3 matrices. Even that will take an entire page. But larger matrices is very difficult. So you'll have to prove it in a different way. We won't go into the proof of those facts. But uh, in some books, that will also be proved that matrix multiplication is associative. Just for example, 5. Then example 6 is a bit interesting. So consider S is the set of irrational numbers along with 1. Okay, so 1 and the set of all irrational numbers. Now, under ordinary multiplication, now 1 times any irrational number is the irrational number itself. 1 times 1 is 1. So 1 is the identity. Multiplication is associative simply because this is associative in real numbers also. It's associative for rational numbers. Then inverse of any irrational number. So 0 is a rational number. 0 is not in this set. Inverse of 1 is 1 that belongs to S. Inverse of any element, any other element, A, in S is 1 over A. And you can check that if A is irrational. So if root 2 is irrational, its inverse 1 by root 2 is also an irrational number. This is root 2 by 2, half of root 2. That's also irrational. So you have an identity, you have that it is associative, and each element has an inverse in the set. Is this a group then? Yeah, yeah. So yeah, so not close. So a lot of the times when we are doing examples and we are looking at different things, we'll assume we won't really go and check the closure property because most of the times it will be closed. But you have to make sure that closure is actually held by the operation. Uh, Closure is actually held in the group. So that binary operation is actually maps two elements to an element in the set. Generally, this is not a problem. But when you get into weird sets like this, weird and unfamiliar sets, then you'll have to pay close attention to check if closure is satisfied. So this is not a group. The next example is so earlier we saw that if we remove 0, Q star is a group under multiplication. Consider Q plus is a set of all positive rational numbers. Or in symbols, if you want to write it, is set of all numbers of the form a by b with a and b both greater than 0 and they are both integers. This is also a group under multiplication. Similarly, R plus, set of positive real numbers. That's also a group under multiplication. But q plus is not a group under addition. That's because under addition, none of the positive numbers have inverse, which is a positive number. So the inverse will not belong to the. So this is another example of a group, and it's another caution that the operation is important. The same set can be a group under one operation, but not a group under a different operation. The next example is so far all the groups that we have seen are all abelian groups. The order of the operation did not matter. The result was the same whether you did A star B or B star A. So then if all the groups have that property, then we would have simply included that as one of the conditions and called that a group instead of an abelian. So since we have separated that out, that means that there are groups where the operation is not commutative. And an example, the most common, so one example is the composition of functions, which is not commutative. Another common example is the following, which is okay. Before going to multiplication, we'll start with addition. The set of all 2 by 2 matrices. Matrices, you know, right? No problem, right? Yeah. With real entries is a group under component-wise addition. Or addition is defined component-wise for matrices. But is it a group under matrix multiplication? Is a set of all 2 by 2 matrices a group under matrix multiplication? Yeah. So if you take the set of all matrices, then not all 2 by 2 matrices are invertible. So the next example, we'll just similar to how we saw for the rational numbers, right? If some element was giving you trouble, you can try to trouble with the inverse part. You can try to remove that element and see if that is a group. And we do that for matrices also. So no, but the set of all invertible 2 by 2 matrices with real entries. For now, we'll stick with real entries, but it doesn't have to be real numbers. This is a group under matrix multiplication. So let's stay at this example for a little bit. So this group is called the general linear group of 2 by 2 matrices over R, and it is denoted by GL2 of R. That is one notation. Another notation is GL of 2 comma R. So this is the notation for the set of all 2 by 2 matrices with real entries and 2 by 2 invertible matrices with real entries. So this is a set of all 2 by 2 matrices can be, we can simply write this as ABCD with ABCD are real numbers, and a 2 by 2 matrix is, any matrix is invertible if the determinant is not zero, right? So in this case, the determinant is simply AD minus BC. So the condition would be AD minus BC is not equal to 0. Now in this group, uh, this, yeah, we have already seen this in school, but I'll just write it out anyway. The operation is the product of two matrices is A1 A2 plus B1 C2 is the first entry, then A1 B2 plus B1 D2, C1 A2 plus B1 C2, C1 B2 plus D1 D2. That is the multiplication operations that we define. Associativity, you can actually do it. You can check by hand since it's only 2 by 2 case. So you can take another matrix A3, B3, C3, D3 and multiply them out and check if you get the same matrix. What is the identity element for this? Okay, what is the identity element in for the addition case? So this is the identity in this case, and the inverse. What was the inverse here for a matrix A, B, C, D? Yeah, for addition it is this. Here for multiplication, what is the identity? Yeah, the n by n, the 2 by 2 identity matrix 1001 is the identity. Because for any matrix A, AI is equal to IA is equal to A. That is from matrix theory. So, and the inverse, there is a procedure to find the inverse. You can either do it through determinants or you can do it through uh, row reduction and Gauss-Jordan elimination. Either way, for n by n matrices, they will have to follow some long procedure to get the inverse. But for 2 by 2 matrices, the inverse of ABCD is 1 over AD minus BC, which is the determinant, times you swap the diagonal entries and you take the additive inverse of the non-diagonal entries. So that would be the inverse. You can verify it if you don't remember. You can still check this and verify that that is the inverse. And so we have associativity that I won't show, but we can show associativity. We have the identity, we have the inverse, and we have to check closure. It is closed. Why is it closed? But these were invertible, right? We also have to show that the product of two invertible matrices is invertible. Yeah, but that is a problem for a linear algebra course. We'll assume that that is true. Or if we define this invertibility from this determinant condition, then another result from linear algebra, again, this is a result from linear algebra. It is determinant of AB is determinant of A times determinant of B. And for integers, the product of two integers is zero only if one of the integers is zero, for real numbers also. So since A and B both have non-zero determinants, A, B also has non-zero determinants. And since A and B are 2 by 2 matrices, AB is a 2 by 2 matrix. So it is also closed. Thus, this GL2 of R or GL of 2 comma R is a group. Now, related to this, another group which is very similar is the set of all 2 by 2 matrices with real entries that have the determinant 1. So set of all 2 by 2 real matrices with determinant 1. This is a group called the special linear group. So non-zero determinants was the general linear group of 2 by 2 matrices over R. Determinant is exactly 1 is the special linear group of 2 by 2 matrices over R. And it is denoted by SL. Here it is GL, general linear. So here it is SL n of R or SL of n comma R. Is a set of all 2 by 2 matrices A, B, C, D, with A, B, C, D being real and the determinant AD minus BC is equal to 1. Now here again you can show closure by the same formula. Determinant of product is the product of determinants, and if determinant of A is 1 and determinant of B is 1, then determinant of AB is 1 times 1, which is 1. So this is also closed. Then the inverse is simply uh, identity is again 1001 because the determinant of 1001 is 1 minus 0, which is 1. Then the inverse here would simplify to simply AD minus BC is 1. So this would simply be D minus B minus CA. So this is another important group called the special linear group of n, n by. Okay, this was actually for 2, so cell 2 of R as cell of 2 comma. Here, just to show that the inverses exist, we started with the example of 2 by 2 matrices, but from linear algebra, we know that uh, using those properties, you can extend this to the set of n by n matrices, square matrices. So in that case, it will simply be called the general or special linear group with of n by n matrices over R. So the 2 will be replaced by n everywhere. And here the AD minus BC will be replaced by the determinant of the matrix. So groups, once we have the group structure, we can once a group has these properties, we can further derive more properties from this just by looking at these group properties. I will show that all of that in later classes. So then you don't have to worry about the exact operation uh, because anything that is true for a general group is true for a particular group also. So if you prove something for a set of integers, say the multiplication is commutative in the set of integers, it need not be true for the set of 2 by 2 matrices, right? There, the multiplication of matrices is not commutative. So when you are dealing with a particular group, there might be properties that are specific only to that group, and then you can't apply those uh, ideas that you have about one group to some other group. But whatever analysis and whatever results we get for a general group G with a general operation star, that you can apply to any particular example. So such general results you'll see in later classes. For now, we are just getting familiar with different type of groups. Later, when we derive those uh, general results, we can also verify them for these examples. We can keep this set of examples, and each time you can go ahead and verify whether it makes sense or not. Another example will, this is the last example for this class. So consider the set Zn. This is a notation for this set. These all the elements 0, 1 up to n minus 1. For n greater than equal to 1, n is a natural number. Zn is a group under addition modulo n. So A mod n. So from the definition of modulo, suppose uh, just recall that if A is Qn plus R, where R is greater than or equal to 0 less than n, we can always divide any integer by n for n positive and write it in the form of Qn plus R. Then A mod n would be equal to R. Now I will leave it as an exercise to verify that Zn is closed under mod n addition. That is, if you add one integer less than n minus 1 and another integer less than n minus 1, less than or equal to n minus 1, modulo n, you will get some integer which is less than n, which will get something. It's kind of obvious, but you can check it yourself. Then the identity in this case is 0 is the identity. So here when I am talking about Zn, I am not talking about the equivalence classes of 0 and the equivalence class of 1 under congruency. I am actually just literally talking about the integer 0, 1 up to n minus 1. 0 is the identity and the inverse of j is n minus j. So, and this group is called the group of integers modulo n. Okay. We have some more examples. We'll do them tomorrow. And once we have maybe like 4 or 5 more examples. Once we are done with the examples, we'll go to some elementary properties, some very basic properties of groups. And then if there is extra time, we'll do some problems. Or if there is no time left tomorrow, we'll do problems in next week. Is that all right? Yeah, I will put them on Drive, Google Drive, and then attach the link uh, in that Excel sheet that I shared. Okay, this spacing is fine for you, or you want me to go fast? Okay, and we'll go at this pace. Tomorrow, more examples and three or four basic properties, then some problems. All right. Good night.